in next example, I will show you how we can design a bias circuit. Okay, for example, we are given a BJT with this output characteristic. So this is IC versus VCE graph of the BJT, and then you want to design a voltage divider bias circuit. Okay, so first of all, you need to be familiar with the structure of voltage divider bias circuit. So this is the structure of voltage divider bias circuit. We have total 4 resistors. Okay, and then we have the single DC supply, so the VCC, and then we have RC at the collector, RE at the emitter, and then we have R1 and R2 is the divider, the voltage divider connected to the base. Okay, so this is the bias circuit that we want to design. And then we have this the VCC we set to be at 15 volt. Okay, and then this is the IC saturation. Then we have the condition IC saturation we want to fix at 5 milliampere. So IC saturation is the definition of IC saturation is the collector current when the VCE is equal to 0. Okay, so if you see the circuit, you have here, this is the KVL of the CE loop, CE current path. Okay, for this is actually the load line analysis. When you do the load line analysis, you assume that the IC and IE is almost the same, and then you can get the KVL here is VCC minus VCC plus IC RC plus VCE, and then plus here the IC is equal to IE, so I put this IC RE equal to 0. So IC saturation is the collector current when the VCE is 0. So when VCE is 0, you know that the IC saturation is equal to VCC over RC plus RE. So this is the equation of IC saturation. And then, but in terms of the graph here, IC saturation is collector current when the VCE is equal to 0. So VCE is equal to 0. So this is the maximum point. This is the IC saturation. Okay. And then because the VCC is given, we can have the plot of the cutoff. So we have the cutoff point is the VCE when the IC is equal to 0. Okay, if you refer to the KVL here, the KVL at the collector emitter loop, when IC is 0, the VCE will equal to VCC. Okay, so when IC is 0, VCE is equal to VCC. VCC is 15, so we have this cutoff point is here. Okay, now since you have these two point, you can draw the straight line connecting these 2 points. Okay, you got the straight line. This is a load line. Okay, so when you want to design the device circuit, the best thing ideally we want to make the Q point of the BJT at the middle of the load line. So for example here, the middle is around here, so I put around here. Okay, so let's say I pick this intersecting point. So I pick the intersecting point here, so I make this is a Q point. Okay, so from this intersecting point you can get the value of VCEQ as well as other parameters. Can also get the ICQ, and this will be your IBQ. Okay, so from the graph I have recorded the value. So the value is ICQ is around 2.3, okay, 2.3 milliampere, and then IBQ is 10 microampere, and VCEQ is around 8 volt. VCEQ is 8 volt. Okay, so you know this one. This is the reading from the intersecting point. Okay, so in the voltage divider circuit, oh, this is a mistake. Okay, in the voltage divider circuit, so I redraw this one. So we have this RC, so we have the BJT here, RC, RE, and then this is R1 and R2. So VCC is 15 volt. Okay, now we want to, and then you know that the VCE here is 8 volt. Okay, how you can get the value of RC and RE? Okay, there is many way. Okay, but the simplest way and the rough calculation is you can use the IC set equation. So IC set is VCC over RC plus RE. So this is equal to 15 RC plus RE, and you know that the IC set is fixed at we set the IC set to be 5 milliampere, and then you get the RC plus RE equal to 3 kilo ohm. Okay, so you need to choose the reasonable value for RC and RE. Okay, for we make some restriction. We want the RC to be 11 times bigger than RE. So we have this restriction. So RC here need to be 11 times bigger than RE. Okay. For your information, usually the RC will most of the time RC will have bigger amount of bigger value compared to the RE. So you can use this equation. You can RC is 11 RE, so 11 RE plus RE equal to 3 kilo ohm. So this one you can solve this one. So you got the RE equal to 0.25 kilo ohm. So now you can get the RC is 11 times 0.25 K. So the RC is equal to 0.25 times 11, 2.75 kilo ohm. Okay, so you got this one. This is 2.75k and this is 0.25k. Okay, next you need to calculate R1. Okay, R2, we set the R2 to be 20 microampere. So this is 20 kilo ohm, sorry, my mistake, 20 kilo ohm. Okay, R2 is 20 kilo ohm. Okay, so how you can do this, how you can analyze the R1, how you can get the value for R1. Okay, so you need to consider the base emitter loop. Okay, so you know for the voltage divider, these resistors connected to the base can be transformed using a Thevenin. So the simplified drawing will be something like this. This is 0.25k. Then we have here 15 volt and 2.75k. So this is our R Thevenin and this is our V Thevenin. So the R Thevenin is defined as R1 parallel with R2. So R1 is unknown. We don't know the value for R1. This is what we want to get the value. So R1 times R2, 20k. So R1 plus R2. For the V Thevenin, the equation is voltage division at the R2. So this is 20k over R1 plus 20k times 15. So here you got this one is 300k over R1 plus 20k. So this is the equation. Okay, when you do the you need to consider the KVL at the base emitter. So the KVL is in this loop. Okay, the base current, you know the base current. The base current is 10 microampere. How about the emitter current? The emitter current can be calculated by adding the ICQ plus from the ICQ plus IB. So it becomes 2.31 milliampere. So this is the emitter current. So we do KVL here. KVL for this one is V Thevenin. V Thevenin is 300k over R1 plus 20k. So this is the supply, so we make it negative, and then this one is plus voltage drop at R Thevenin, which is IB times R Thevenin. IB is 10 microampere, but usually I will use the ampere unit, so I convert it because 0.01 milli times R Thevenin is R1 20k over R1 plus 20k, and then we have here this is voltage drop at the base emitter, so this is 0.7, and voltage drop at 0.25k, which is 2.31 milli times 0.25k equal to 0. Okay, so you need to in this KVL you have only R1 as your unknown parameters, so you can solve it. So when you solve it, let's say we solve term by term, okay, you will get something like this. This is R1 plus 20k. The first term is okay, actually we can rearrange this. We can get 300k minus 0.2, this is 0.21 R1, and then this one is equal to 1.2775. Okay, so you got this one. So this one is 300k 0.2 R1 equal to 1.2775 R1 plus this one is 28.875k. So you got this one. This is 1.4775 R1 equal to, so this is 200. Okay, is it just, you got this one is 274.45 k, and then you got the R1 is equal to 185.8 kilo ohm. So you got all the value. So your design will be something like this. The R1, and you have the R2 ground here. R1 is 185.8 kilo ohm. R2 is fixed at 20 kilo ohm, and then you have here the BJT here. The RE is 0.25 kilo ohm, and RC is 2.7. Much is it? 2.75 kilo ohm. And then the VCC is 15 volt. Okay, so this is the design, how you can design your voltage divider. So this type of question, this is the design question. It will take longer time. So but this is very useful for you in order for you to design the amplifier circuit. Instead of in the test and in the final exam, usually the bias circuit is given and then you need to solve the Q point, but now the flow is opposite, where we start from scratch. We want to design, we want to build our circuit.